Take a phrase in English like European Economic Area. To translate that into French, the structural grammar must completely flip. The noun, area or zone, moves to the front, while the adjectives slide to the back, zone économique européenne. A human translator naturally scans back and forth across the sentence to place the right word in the right spot. To replicate this, a machine must learn to jump backward and forward across a sequence of text, rather than processing it word for word. Before 2014, the standard approach in artificial intelligence was a sequence-to-sequence model, often called an encoder-decoder. One part of the network reads the input sentence, and the other part writes the output. The encoder communicated by compressing the entire English sentence into a fixed-length context vector, a single mathematical array of numbers. This forced every meaning, whether 3 words or 30, into one rigid mathematical bottleneck. While this works for short phrases, cramming a 50-word sentence into that same vector causes the model's memory to fail. By the time it processes the final word of a long paragraph, the mathematical representations of the earliest words often fade into noise. Accurate translation requires a system to hold the entire text in its working memory, actively choosing which specific words matter at any given moment. A solution arrived in a 2014 paper by researchers Dmitry Bogdanov, Kyung-Hyun Cho, and Yoshua Bengio. They introduced a method to jointly learn to align and translate. The first step of their architecture upgrades the encoder using a bidirectional RNN. An RNN, or recurrent neural network, is a model that processes data step by step in a sequence. This new encoder deploys 2 separate networks to read the sentence from left to right and from right to left simultaneously. As these 2 passes cross, the model creates an annotation for every single word. An annotation is a mathematical vector that absorbs the identity of the word and the context of the words immediately surrounding it. The annotation for the word area now carries the mathematical signatures of its neighbors, European and economic, directly within its vector. By blending these inputs, the AI transforms a static line of text into a rich landscape of connected meanings, preparing it for the French translation phase. To generate the first French word, the decoder surveys the entire landscape of annotated words, rather than relying on a single bottleneck vector. It uses an alignment model to run a real-time calculation, determining which English words are most mathematically relevant to the specific word it is about to generate. The AI assigns a percentage weight, called an alpha value, to every source word. To produce the French word for area, the alpha value for the English area spikes toward 100%, while the rest of the sentence receives very little weight. Graphing all of these percentage weights together creates this visual matrix, a map of the machine's attention during the translation process. At the intersection of the French word zone and the English area, the stark white pixel indicates a massive mathematical reaction. The nuance in the shading shows that while area is white, European and economic have a faint gray glow. The model is pulling a fraction of the weight from those neighbors to build a custom context vector for this specific word. After outputting zone, the model discards that context vector, surveys the English sentence again, and recalculates the weights for the next word from scratch. This dynamic scoring allows the AI to precisely choose where to focus its attention at every millisecond of the process. The literal stress test data from the 2014 paper reveals the macro impact of this mechanical shift. With the old encoder-decoder architecture, translation accuracy plummets as soon as a sentence crosses the 20-word mark. The bottleneck simply cannot hold the data. In contrast, the attention mechanism maintains a stable score, even when processing sentences extending past 50 words. This method for capturing long-range dependencies revolutionized computer vision as well, allowing models to correlate pixels in completely opposite corners of an image. This 2014 innovation paved the way for the 2017 Attention is All You Need paper, providing the mechanical foundation for all modern generative models. When today's AI writes an essay or generates a photorealistic image, it functions by dynamically weighing the importance of every piece of information it has ever seen, one micro-decision at a time.